Okay, so section 7.1, theorem 7.14. So this is an important one. It was important enough to put on your exam. And so we have if x1 and x2 are corresponding eigenvectors of distinct eigenvalues lambda 1 and lambda 2 of a real, now both of these things have to be true here, real symmetric matrix. So it has to be real valued entries and the matrix needs to be symmetric. Then x1 dot x2 is equal to 0, or in other words, they are orthogonal vectors. So, you know, that's very nice, and so I'm not going to go through the proof. They do a nice proof in the text. And so then what that leads to, though, is since we've got that orthogonality and so forth, then when we get to theorem 7.1.5, we have that and this again is, they say for a 2 by 2, but it's just generally true. So, you know, let A be a real symmetric matrix. So I don't care what its dimension is. So it's a real symmetric matrix with distinct eigenvalues lambda 1, lambda 2. Okay, then we can write A as P D P transpose for P a proper orthogonal matrix. Okay, so we can diagonalize it this way, but you know, so we knew we could diagonalize it with distinct eigenvalues, but if it's symmetric, when we diagonalize it, we can choose our eigenvectors to be unit vectors, and they will be orthogonal to each other. And so our P inverse that we would usually write, we can just do with a P transpose. Okay, so is for P a proper orthogonal matrix, and D, and this should go up to lambda n for us, and D a diagonal of lambda 1, lambda 2, up to lambda n. So that is pretty awesome. Okay, so any real symmetric matrix, with distinct eigenvalues, we can do this type of decomposition. And so that's very nice, and so pretty much that means, if we are in the 2 by 2 case, P is a rotation matrix, okay, which they point out. Okay, and let's toss in their example. Example 7.1.1, and here they say, let's let A be the symmetric matrix, 12, minus 6, and 7. They get the characteristic polynomial, so we would have 12 minus lambda times 7 minus lambda minus 36. We set that equal to 0. They tell us that's lambda squared minus 19 lambda plus 48 is equal to 0. And so we get, they can factor that as lambda minus 16 and lambda minus 3 equals 0. So lambda is 16, or lambda is 3. So there are our two eigenvalues, and so they are distinct. They get the eigenvectors. So let's take a look at least one of them. So we had 12 minus 6. So let's do 12. We'll do the 3 here. Minus 3 and a minus 6. Augment that with 0, 0. We don't really have to show the 0, 0. And then a minus 6 and a minus 3, 3, and a 7, right? Yeah, 7. So 7 minus 3. And that augmented matrix then becomes 9 minus 6, 0, minus 9, oh, no, minus 6. Gosh, sorry about that. Minus 3. We don't want that in there. So minus 6 and a positive 4 and a 0. And, I can see that if I multiply the top by 2/3 and add to the bottom, I get zeros across here. So those are just zeros. And so, I have 9x minus 6y equals 0. And, I can write that probably in lowest terms with nice integers. If I let x be a 2 and y be a 3, I'll get a 0. So here my eigenvector, I'll call it x3 like that. I could do that as a 2 and a 3. And I believe that's what they have. Yes. Now, similarly for if I look at the eigenvector for 16, I end up, I guess, I can write that as minus 3, 2. Now, those are not unit vectors, so I need to make them unit vectors. And so my x3 as a unit vector, so I'm going to call that a u3. I've got here, if I square these, 4 plus 9 is 13, so I need to divide by the square root of 13, And so this is 2 over the square root of 13 and 3 over the square root of 13. And 16 is the same magnitude, so my U16, my unit vector for that is negative 3 over the square root of 13 and 2 over the square root of 13. Now notice back here, it's pretty obvious that x3 dot x16 is equal to 0. I get a negative 3 times 2 and then plus 2 times 3. And so I do indeed get 0, so they are orthogonal to each other. And put that right there. Okay. So they are orthogonal. And so I can set up my matrix. Now the only thing I have to be careful of is I need things in the right order. So in their case, they are writing D as the largest eigenvalue first. And so our P better have the corresponding eigenvector first. So minus 13 over the square root of 13 and 2 over the square root of 13. And then 2 over the square root of 13 and 3 over the square root of 13. And there is our D and our P. And so that says that I could write my A as P, D, P transpose. Okay. And again, I know they're unit vectors and I know they're orthogonal, so I know P times P transpose does give me I. So that's a nice little example. And there we go for that piece. And we'll call that done.